Hello and welcome. Today we are going to be talking about different probabilities. Now, some of these probabilities are a little more complicated than ones we might have looked at in the past, and we're going to be using the different counting methods that we've looked at in order to find these probabilities. So far, we've learned three quick ways of counting the total number of outcomes using a variety of different scenarios. The fundamental counting principle says that we can multiply the number of outcomes for each event in a scenario to find the total number of possible outcomes. Permutations are ordered arrangements of R items chosen from a group of N. We also use this NPR notation for that. Again, this is when order matters. So these are things like when you're running a race, how many ways could the medals be handed out, right? When you're running a race, when you're arranging something, when you're lining up, anything that has a position involved, that's when order matters, and that position is a permutation. Combinations of R items chosen from a group of N items, well, again, that's NCR instead of NPR, where no items are used more than once and order doesn't matter. These are things like whenever you see a group, a team, or a committee. The main idea is that with permutations, order matters, and combinations, the order doesn't matter. Now, when we go to calculate probabilities, one of the things that you should already know is that the numerator of a fraction represents the total number of outcomes within the desired event. So like that's what you want. This calculation often requires using more than one counting method. The denominator of the fraction represents the total number of outcomes possible, and that's known as the sample space. This is often simpler than the numerator, and you'll see a few examples as to why I might say that. So let's start out by looking at some examples and seeing how we can use the counting principle, permutations, or combinations in order to calculate some probabilities. A bike lock uses four distinct numbers chosen from 0 through 9, and no number can be repeated. What's the probability that the lock code will consist entirely of odd numbers? Well, the first thing that we want to make sure we understand is that if it's 0 through 9, then that means that there's going to be 10 elements in our sample space. I like to write them out sometimes just so that I can kind of remind myself what I'm working with. Now, we can use the counting principle to do this as well. Consider this, the number of items in our event space, right? What we want. We could say like, well, it's a four distinct numbers and they're chosen from 0 to 9. And so then that would just be, I have 10 numbers to choose from for the first one. Because this says no number can be repeated, right? This is without replacement. So that would be 10. And then once I pick one for my first number, I can't choose that again. So then it would be 9, and then 8, and then 7. Now, the total number of, so this is the total number of ways of choosing four possible numbers. That means that's not actually my E. That should be that would be S. There we go. So that's going to be the bottom of our fraction. That was pretty easy. That's just the total number of ways that we can choose four numbers without any repetition. Now what we want to do is, now we got to do the E. The E part of this, or what we want, is we want this to consist entirely of odd numbers. So our event is odd numbers. And if we consider that, when I look and see how many odd numbers I have in this, I have 1, 3, 5, 7, and 9. You can see we have a choice of 5 odd numbers to choose from. So I would have 5 numbers to choose from for the first position. I would have 4 numbers to choose from for the second, and then 3, and then 2. Now, if I multiply these all together, and I treat this as a fraction. Remember, probability is just what you want over the total possible, or the number of elements in your event divided by the number of elements in your sample space. So I can do this as 5 times 4 times 3 times 2, and that gets me 120 on top. And then on bottom, I've got to do 10 times 9 times 8 times 7, or 5,040 on bottom. Now, it's also a good idea um, to simplify these fractions, right? So we could do 120 divided by 5040, and we get that. Remember, if you click this little button over here on the right side of that decimal number, you can flip back and forth between the decimal and the fraction. So this is a 1 in 42 chance. Now we could also use some other mathematical notation for this. When we look at our numerator and our denominator, I'm going to do the denominator first. The total number of items in our sample space, we have 10 numbers to choose from, and we're going to choose 4 of them without repetition, right? Because it says no number can be repeated, and the order matters. That's why it's 10p4. In the numerator, we have 5 numbers to choose from because we're only choosing the odds, and we are going to pick 4 of them. Now, that really does come out to be the same thing. And we can check that in Desmos as well, just by using the NCR and the NPR. Remember, that's under function, and that's where we have NPR and NCR. So let me slide this over to the other side so we can see it. And we'll do 5 comma 4. That's my numerator. And then we'll divide by, there you are, 10p4. So we'll use NPR and we'll do 10 comma 4. And you can see we do get that same decimal, and if we change that over, we still also get 1 out of 42. So that's the likelihood of randomly choosing a lock code that consists entirely of odd numbers where repetition is not allowed. In a raffle game, a person must correctly choose 5 numbers out of 48 where the order of the numbers does not matter. So as soon as I see that, I'm probably going to highlight that. I want to make sure that I remember the order doesn't matter. If one winning ticket is selected, what's the probability of winning? Well, let's do the denominator first. The denominator is usually the easiest thing to think about. 5 numbers out of 48 where the order doesn't matter. So that means then that we are going to be using a C, right? Because this is a combination where the order doesn't matter. So the number of elements in our sample space is going to be 48C5. Now, I do often have people ask me, how do you know that it's 48C5 and not 5C48? Well, the first number represents the total number you have to choose from, and the second is how many you're going to choose. The good news is if you do get those switched around when you put them in the calculator, it doesn't work out for you. You won't be able to get it. Now, as far as the top goes, this might seem a little bit strange, but it's actually going to be 5C5. You might say, wait a minute, I understand where 5 came from. We're choosing 5 numbers, right? We're choosing 5, so that one makes sense. But why do we have a 5 in the front here? That's because these 5 numbers are the subset of the winning numbers. If there are 5 winning numbers, let's say the winning numbers are like 17, 23, 42, 1, and 9, right? If those are the 5 winning numbers, out of all of the numbers from 1 to 48, then what happens is I want to actually choose these 5 numbers. So that's a subset of the all 48 numbers. And so I want to choose those 5. So out of those 5, I have to choose all 5. That's why it's 5C5. Now, another way to consider that is it's really just going to come out to be 1, right? There's one winning ticket. There's one way to win, and that's to have all 5 of those numbers chosen. So when we do this, then this numerator is going to come out to be just 1, and the denominator is going to come out to be a fairly large number. So we'll do NCR, and we'll do 48 comma 5. And that's it. And just in case you wanted to check me on this, we can definitely do NCR, and we can do 5 comma 5, and you'll see that there is really just one way. If you have 5 numbers to choose from that are winning numbers and you want to choose all 5 of them, there's only one way to do that, and that's to have all 5 of them. So what's the probability of winning? 1 in about 1.7 million, because we have our 48C5 in the denominator. An improv sketch shows, or an improv sketch show asks each audience member to write a topic on a piece of paper and put it into a hat. The host then chooses 3 of the topics randomly to use for the show. Okay. If 10 men and 15 women each submit a topic, find the following probabilities. All 3 topics were written by women. So let's first do our bottom. This is the number of elements in the sample space. This is the total number of ways from all the people, right? And we're going to look at 3 of them. Notice that they're choosing topics, and it doesn't really seem like the order matters. They're just going to choose 3 topics at random to use in the show. So it doesn't really matter the order. That means that we are going to look, and we notice we have 10 men and 15 women. That means 25 total people. And what happens is we want to choose 3 of them. So the bottom of this is going to be 25C3. That's the total number of ways of choosing 3 topics from this audience of 25 people. Now, the event that we're looking for the first one anyways, is all 3 topics chosen by women. That means that we want to only look at the women for this one. And again, order still doesn't matter. Notice that we have 15 women to choose from, and we want 3 of them. So 15C3 over 25C3. And to be honest, like, to a math person, that's pretty good. Like, as far as just writing it like that. We're going to use calculators so we can get something that's a little more tangible to everybody. But we'll do 15. Oops. Let's go ahead and get our NCR and 15 comma 3. So our numerator is 455. And our denominator then, we go 25C3, is 2300. We could divide those separately, or I can just type it in as 455 divided by 2300 and have Desmos reduce that for us to be 91/460ths. If you like the decimal, that's fine, because a lot of people do prefer thinking about this as almost 20%. Now, 91/460ths is kind of a nicer, more accurate, or I should say more precise way of expressing it, because it's the exact answer. But also understanding that this is about 20%, that's pretty good too. Okay. Next, let's look over here. All 3 topics were written by men. This is a good one for you to just go ahead and do, pause the video and do it, because it's very similar to the one we just did. Let's go ahead and finish this though. So the number of elements in our sample space, again, there's 25 people and we're going to choose 3 of them. That's the total number of ways for this to happen. The number of items in our event this time is going to be all 3 topics written by men. You can see that we have 10 men to choose from, so this will be 10C3. So 10C3 would be what we're looking for this time. That's going to be our numerator. That's 120. And our denominator is still going to be 25C3, which we already figured out was 2300. So we'll just put that on bottom. We can have Desmos do a little bit of calculation for us in order to clean this up. 120 divided by 2300, and that gets us about a 5% chance. If we tap that little button next to the decimal, this gets us a nice fraction, 6 out of 115. So there's a significantly better chance of having all three topics chosen by women than by men. And let's make sure we understand why. That's because there are significantly more women than men. You might say, oh, but there's only 5 more. Yeah, but it's 50% more women, right? There's 10 men and 15 women. That means for every 2 men, there's 3 women. So you are much more likely to have all 3 topics chosen by women. What about exactly 2 topics were written by men? Well, the good news is that the bottom doesn't change. It's still going to be the total number where we have 25 people and we're choosing 3 of them. But our event this time is going to be a little bit different. So 2 topics written by men, but we're choosing 3, right? And so here's what we actually have to think about this for a minute and say, listen, if we want 2 topics chosen by men, then that means that exactly 1 topic is chosen by a woman, right? And this is like an and. We say we want 2 topics chosen by men and 1 topic chosen by a woman. Remember, when we do and, that's our multiplication. So we'll look at our men first, and we'll say that we have 10 men to choose from, and we're going to choose exactly 2 of them. And then we've got to extend this out and say, you know what? We also still need 1 topic written by a woman. So that will be 15 women to choose from, and we want exactly 1 of them. Notice here that here's the 2 that the men chose, and here's the 1 that the woman chose, and that gets us a total of 3 topics chosen. Our denominator isn't going to be any different. It's still 25C3, and so that will be 2300 on bottom. And then on top, we've got to do 10C2 times 15C1. 10C2 is 45. And 15C1 is actually just going to be 15, but I will verify it for you. So, oops, too far. Also because sometimes I mess up and make silly mistakes, so I always like to double check myself. So that means we have 45 times 15 in the numerator, which is 675 over 2300. And then after that, we'll go ahead and we'll divide that by 2300. That's about a 30% chance, which is 27/92 to be more precise. So pretty decent chance of that happening. Once again, we had 2 different things we had to cover. The first was the fact that we wanted exactly 2 topics written by men, and if we want exactly 2 by men, that implies that we need a 3rd topic, or in other words, 1 more that's written by not a man. And in this case, that's our women. Okay. The last one here, more topics written by a woman than by a man. So let's look at all the possibilities. We could have 3 topics written by women, or 3 women and 0 men. We could have 2 women and 1 man. We could have 1 woman and 2 men, or we could have 0 women and 3 men. And what we've got to do is identify which ones are going to work for us. So the first one here, 3 women, 0 men, yes, that meets the criteria, more women than men. The next one, 2 women and 1 man, yes, that also meets the criteria of more women chosen than men. The next one, though, 1 woman and 2 men, nope. 0 women and 3 men, nope. Those ones are no good. We don't even want to consider those. They don't meet our criteria. So we do have 2 different possibilities, though. Either one of these will work. This one would work, 3 women and 0 men, or this also meets it. We could have the choice of 2 women and 1 man. That also meets it. And remember, an or means that we're actually going to be adding these probabilities together. So let's start off with the 3 women and 0 men. You know what? We actually already did that one. We did that one up over here. All 3 were women. And so you'll notice that this is just going to be 15C3 over 25C3. And then for the second one, 2 women and 1 man, it's a lot like what we did on the previous one on part C, 2 men and 1 woman. Except here, we're going to say that we have 15 women to choose from and we want 2 of them. And there's 10 men to choose from and we want 1 of those. The denominator will still be 25C3. Remember, because either one of these will work for us, the first one or the second one, we're actually going to add these probabilities together. And this is a nice mathematical way of writing our answer, right? So the first one, 15C3 over 25C3, I'm going to write that as 455 over 2300. Sure, I could write the reduced form, but watch for just a second. You'll see why I don't. Next, we do 15C2 times 10C1. We can go to our calculator and get that all put in here. So 15C2 times 10C1. This time I decided to put it all in there so you can see you could do this in one go, right? And that is 1050. And look, the bottom is also 2300 because it's 25C3. Now, the reason why I wrote these separate is so that you can actually see the first one is the probability of 3 women and 0 men. Okay. And it says that, listen, that one works. Or if we have 2 women and 1 man, and that would be this individual probability. Okay. And that one also works. And because they have the same denominator, we can really just add those together. I actually don't even really need a calculator for that. Don't get me wrong, I'm going to use it because I'll make plenty of mistakes. But we could add those together and say that that's going to be, I think it's 1505. Guess what? I'm definitely going to check though. So we'll take, let's clear that out, and we'll do 455 plus 1050. We get 1505. And then we're going to take that 1505 and divide it by 2300 in order to simplify it down and make it a little bit cleaner. And that's 301 over 460. Notice that it is a significantly higher chance for that to happen than all 3 topics written by women. That's because all 3 topics written by women, like in part A, is actually just part of this answer, right? That's just this. And then we're going to add to it. We're going to add to it the likelihood of 2 women and 1 man. So we get a pretty high chance of this being the case. I do want to point something else out before we move on, and that is that each time, notice that here we're choosing 2 from the women and 1 from the men, and that's what makes our 3 total choices. Okay. Next, Christina, Richard, Monica, and Andrea are competing at bowling. Assume that all possible score orderings are equally likely. That just means that they're all pretty much the same skill at bowling. It's not like one of them's a professional bowler and is much, much more likely to always come in first place. We're just saying, they're all pretty well the same probability of winning. What's the probability that Christina scores the lowest? Well, I'm going to show you kind of two different ways to think about this. The first way, what's the probability that Christina scores the lowest? Well, if she's bowling with four people and they're all equal bowlers, then guess what? She has a 1 out of 4 chance of being the worst bowler. There's 4 bowlers, she's one person, 1 out of 4 being in last place. She also has a 1 out of 4 chance of being in first place. Okay. So some of these you really can just kind of reason out like that. But let's go ahead and look at maybe some of the math behind it, and you're gonna say, why are you complicating this? Well, it's just important to understand with all of the countings. Assume all score orderings are equally likely. Well, this is a place where there are positions we have coming in first place, second place, third place, fourth place. You can see it even says orderings, right? They're competing, so first place. So the total number of items in our sample space is actually going to be 4p4, right? We have 4 places to choose from, and any one of the 4 could come in first, and then someone else could come in second, and someone else could come in third, and someone else could come in last. Now, for our event, though, what this is for Christina to score the lowest. If we are guaranteeing that Christina is going to score the lowest on this, then we know that, like, you could think of it like this. This one here is locked in with Christina. She's guaranteed to be in last place if this is what we're looking for. In which case, we have 3 different people could come in first place, 2 different people could come in second place, and 1 could come in third place. This really means that you have 3 people, and we're going to choose all 3 of them for all of the other places. So we kind of have the math notation way of writing this right here. And then we have the numbers written out here. By the way, if Christina's in that last spot, just because this is bothering me to write Christina there, it means that she's guaranteed there's only one person there. So we'll put a 1 there. Now, there's also hopefully a number of you that are looking at this and saying, oh, but I see if I have a 3 in the numerator and a 3 in the denominator, those will divide out from each other. 3 divided by 3 is 1. 2 divided by 2 is 1. 1 divided by 1 is 1. And you can see that what we're left with is 1 in the top and 4 in the bottom, or 1/4, just like we said a little bit ago. So that's kind of a little bit more complicated, or I should say maybe a little more detailed reason as to why it's just 1/4. What's the probability that their scores match the order that they bowl in? Okay, well, just like before, the number of elements in our whole sample space, or in other words, the total number of ways that they could be arranged, is 4p4. And 4p4 means 4 blanks, 1, 2, 3, 4, start with 4 and go all the way down. 4 times 3 times 2 times 1, which of course is just 24. Now the number of elements in the event space means that we very specifically want Christina first, Richard second, Monica third, and Andrea fourth. There's only one way for that to happen, right? And that is if Monica comes first, Richard comes second, or sorry, Christina comes first, Monica, oh my gosh, I can't read. It's in that order. 1, 2, 3, 4. There, now I can't mess it up. And so there's only one way for that to happen. That's why the answer here is just 1/24. So there's 24 possible ways for this to happen, and only one of them has Christina, then Richard, then Monica, and then Andrea. This is kind of like doing the counting principle. How many different people could come in first? Only Christina. How many different people could come in second? Only Richard. How many could come in third? Only Monica. And only Andrea could come in fourth. So this is just using the counting principle of saying how many do we have at each choice. Okay. A bag contains 9 blues, 4 orange, and 7 purple marbles. What's the probability of randomly drawing 2 marbles at once and they are the same color? So let's just find the probability. We're going to do these one at a time. We're going to find the probability of drawing 2 blue marbles. So we've got 9 blues to choose from, and we're going to be choosing 2. This is the blues. Now let's look at the total number of items in our whole sample space. When we look at this, I see there's 9 blues, 4 orange, 7 purple. That's a total of 20 marbles. So there's 20 marbles to choose from this bag, and we're going to pick out 2 of them. That's where we say 20C2. Notice they're chosen at once, which means the order doesn't matter because we're just taking them out at like a handful of marbles. So the order doesn't matter. It's just a handful of things. And this is the probability of choosing blue marbles. Okay. Next, let's look over to the orange marbles. You can see we have 4 oranges to choose from, and we want to actually choose 2 of them. But keep in mind, the probability of choosing 2 orange marbles exactly is, there's our numerator, there's still 20 total marbles to choose from, and we're going to choose 2. Remember, it's not like we've already, this isn't doing a probability where like, hey, let's take out 2 blue marbles and then take out 2 orange marbles and then, no, this is just saying like, hey, what's the probability of reaching in the bag and pulling out 2 oranges? That's it. Lastly, we'll do purple. And we can see there's 7 purples to choose from, and we want 2 of them. Keep in mind that there's 20C2 possible ways for that to happen. Next, we're going to go through and calculate all of these. So 9C2 over 20C2. There's 36 ways for us to get 2 blue marbles. And then for the 20C2, there's 190 total. For the orange, we have 4C2 to be 6. That will also be over 190. And 7C2, I think that's 21. Yeah. And that's also over 190. Now, because any one of these is a possibility, we can just add them all together. We'll add our 3690ths plus 690ths plus 2190ths to get 63 190ths. And that, I don't believe, reduces. We'll find out though. So we have that, and if we hit our fraction button, notice that it just stays the same. That means it is done just like it is. Now, instead of doing these all separate, you could also think of it like this. You could write it as 9C2, that's the total number of ways of choosing blues, 2 blue marbles, plus 4C2, that's the total number of ways of choosing 2 orange marbles, plus 7C2, that's the total number of ways of choosing 2 purple marbles, and that's over 20C2. This is kind of a little bit cleaner way of doing this. Again, the numerator gets you the total number of elements in our event, what we want, which is 2 of the same. And there's 3 different ways for us to get that. Either 2 blues, 2 oranges, or 2 reds. Any one of those would be winners. And then the total number of ways of choosing 2 marbles, of course, is 20C2. All right, this is our last problem to look at today. A concert venue is staffing an outdoor music festival with 24 available workers, 9 stage crew members, 10 security staff, and 5 sound technicians. For the event, they want to choose 8 workers. So there's only 8 people going to be working this event. And for some strange reason, they're just throwing all the names in the hat and hope that it works out. This is probably not a good idea. But it's fun for us to calculate what's the likelihood it's going to work out for them. So they're going to choose 8 workers. Determine the probability that exactly 3 people chosen are stage crew members, that they end up with 3 security staff, and that they end up with 2 sound techs. So that's what we want to happen. And this is a just for fun situation because this, of course, is fun. When we look at our number of elements in our sample space, there are a total of 24 people, and we're going to choose this group of 8 individuals to work for us. Now, the number of elements in our event, what we actually want to happen, that's this right here. That we end up with 3 stage crew, that we have 3 security, and that we have 2 sound techs. That's what we are trying to find, the likelihood of that happening. So let's take these one at a time, and we'll start out with 9 stage crew members, and we want 3 of them. So that's 9C3. Next, we're going to do the fact that there are 10 security staff, and we want 3 of them. So again, we want a group of 3 of them, and that's why we're using the C notation. Lastly, we're going to get our sound techs. We have 5 sound techs to choose from, and we're going to hope that we get 2 of them. So that'll be 5C2. Now, notice here, we're going to multiply these together because these are the 8 people that we want. You can tell because we have our 3 stage crew, our 3 security staff, and our 2 sound techs. And those 8 people all add up to be the group of 8, right? 3 from the one group, 3 from the second group, and 2 from the third. That's where we get our 8 people from. Next, we're going to go to the calculator and figure out some of these numbers. You could put this all in one go if you wanted. I'm going to choose to probably separate these out a little bit just so that we can have them written. We can see there's going to be 84 crew members. Then for the security, we're going to also do 10C3. That's 120 from them. And then for our sound techs, we've got 5C2, which should come out to be 10. There's our 10. And then our bottom number is going to be pretty sizable. That's going to be our 24C8. Ooh, that's a big number. There we go. And now we'll just multiply our numerator and then divide it by our denominator here. There we go. We get a little over 100,000, over 735,000. So we'll take that answer and we'll divide them and work on reducing them out. So about a 13% chance or 14% chance that this works out. Now, that's not a real high chance, which is also one of the reasons why we don't just throw all the names in the hat and hope that it works out, right? The likelihood of it working out is not good. It's only about a 14% chance that you end up with a group of people that will work for for your situation. And so remember, whenever we're calculating these, it's usually easiest to figure out the denominator first. That's what I like to do. That's the total number of ways in the sample space, and then figure out your individual situation. Sometimes you're going to be adding things together, like in the previous problem, where we have to say like, oh, this will work, or this one also works, or this one also works. And whenever you're thinking of that or is when you're going to be adding them together. Okay. Or in the bottom case, we need all of those individuals to be the case. We need to have 3 from the first group, and we need 3 from the second group, and we need exactly 2 from the third group. And that's why we were multiplying them. So I hope this helps out a little bit with some probabilities. These are tricky, so please make sure you do them a couple times over in order to um, in order for this to work out for you. All right, keep practicing.